I have planned to deliver the full course on quantum mechanics. I am basically using the book Griffith Third Edition Introduction to Quantum Mechanics. Today we are going to see the development of the wave function, a conceptual and historical overview of the quantum mechanics. In this lecture, we are going to see in detail the wave function and why we have to normalize the wave function, what is the significance of the wave function in detail. First, we will see some historical background. In 1900, Planck quantized the energy to explain black body radiation. So, actually, this is the birth of quantum mechanics. He said that energy is quantized with a multiplicative factor H cross. H. At that time, it is H. H divided by 2 is H cross. So, H is the Planck constant. In 1905, Einstein explains the photoelectric effect using light quanta. That is, he explained the photoelectric effect light act as a particle. So that is the Einstein explanation for photoelectric effect. In 1924, the de Broglie hypothesis, which is very important, he introduced the concept of matter waves. That is, particle behaves like a wave. In 1926, Schrödinger formulated the wave equation, which we are going to see in detail in this class, and the Fawn interpretation for the wave function, that is modulus square of the wave function, is probability density. We will see in detail. The de Broglie hypothesis plays the important role in quantum mechanics. Uh, According to him, the particle like electron have wave property. That is very important. And the wavelength associated with the particle is equal to, that is lambda is equal to h over p, where h is the Planck constant, p is the momentum. Inspired by the 2L nature, he proposed this hypothesis. And now we will see about the Schrödinger equation. In Schrödinger equation, normally we are using energy operator E, which is equal to IH cross delta over delta T, and the momentum operator P, which is equal to minus IH cross delta over delta X. The time dependent Schrödinger equation is IH cross delta psi over delta T, which is equal to minus H cross square over 2m delta 2 over delta x2 plus v of x multiplied by psi. Here, this is the kinetic energy. This is Ke, kinetic energy, and this is potential energy. So naturally, this is wave function. So if you add a kinetic and potential energy, you will get the Hamiltonian operator. Hamiltonian operator is nothing but sum of the kinetic energy operator and potential energy operator. So the time dependent Schrödinger equation can be written as IH cross delta psi over delta t is equal to H psi, which is a function of x and t. Now we will see the physical interpretation of the wave function. Psi of x and t is a complex function describing the quantum state. It is a complex function. And modulus psi of x and t square gives the probability density. For example, let us say your wave square of the wave function, y-axis is modulus square of the wave function with respect to the distance x. Here I am selecting a small length element tx. So this gives the probability density between the point A and B, that is between the small length tx. Uh, Fortunately, in order to find the probability, we have to integrate modulus psi squared with respect to tx. So x is having the distance of length. This is L. So naturally, what is the dimension of psi? Psi is 1 over square root of L. Then only if you take square, you will get 1 over L and L will get cancelled. This is the dimensionless quantity because probability is basically a dimensionless quantity. It varies 0 to 1. This will give you the probability density. We will discuss what is probability density in later stage. Here in this case, in the case of one dimensional particle, this probability density is modulus psi squared over a length. So because this psi unit of psi is 1 over square root of length. So the probability density per unit length. Now we will see some of the important properties of the wave function. First, the wave function must be a solution for a Schrodinger wave equation. That is the foremost important point. So it must be the solution to this Schrodinger time dependent equation. I will come to it later. Superposition, and that is linear combination of, if psi is the solution to this Schrodinger wave equation, then any linear combination of psi also the valid solution. Then why we are calling this as a linear combination? This, the time dependent equation, Schrodinger equation is I h cross delta psi over delta t, which is equal to h psi xn t. Here you can see psi is linear. It's not psi squared, non-linear. There is no non-linearity. Let us say psi 1 and psi 2 are the solution of this Schrodinger equation. Naturally, the C1 psi 1, any linear combination, also the solution of same Schrodinger wave equation. We are going to deal this in detail when we are dealing both the theory as well as the problem. So now we will move further the important properties of the wave function. So the other important properties are the wave function must be normalizable, that is square integrable. That, that is integral modulus I squared dx must be equal to 1, and wave function is not directly observed. That is another important point. So first we will look into the matter of normalization. Let us say you have a wave function, Gaussian wave function like this. You are taking 2 point A and B. This shaded area gives you the probability density. Sorry, if you integrate this over this area, you will get probability. So Px is probability density. As I said, P of x is probability density per unit length. So let us say this probability density, P of x probability density tends to zero point 0.5. Just for example I am giving. So the length, if you see, this is one dimension, so you have to take only the length, change in length between A to B. If it is very small, let us say in our case it is 0.1. So what is the probability density? Probability density, that is probability, this is the probability 0.5. Probability density is probability per unit length. So 0.5 divided by 0.1, which is equal to 5 naturally. So, if you take the integral, if you integrate this, you must get 1, but you will not always get 1. So, in this case, it may be 5. So, we are introducing a constant called normalization constant A, this will take care of that total integral will be 1. So in this case, what must be the value of a? Value of a is equal to zero point 0.2. So if you multiply zero point 0.2 and 5, you will get 1. So now it is normalized, because if you take a very smaller length, your probability density will be the higher. So you have to normalize it. This is the concept of normalization. We are choosing a parameter, scaling parameter, such that if you multiply this and this integral, it must be equal to 1. The wave function must be a continuous one and smooth. That is, a wave function and its derivative must be a continuous one. So, and it must satisfy the boundary condition. So, we are going to see the case of infinite square well potential. So in the case of infinite square well potential, the wave function vanishes as at the boundaries. So when n equal to 1, the wave function will vanish both the boundary. And if n equal to 2, that also it vanishes at the boundary. However, the frequency is doubled. If frequency is tripled, n is 3, that case also it must be 0 at the boundary, and this 0 continues till infinite, because outside the wall also. So this is the meaning of continuous one. So the derivative wave function and its derivative must be a continuous one. So what is the density of this wave function? Just to square it, you will get like this. So it carries the complete information, that is all observable derives from the wave function. So this is the best example. That is the reason why we are giving more importance to infinite square well potential, which we are going to see in due course. Some more important properties are: the wave function must be single valued in order to physically unambiguous. That is, the wave function must be single valued in order to be physically unambiguous. This means that for any given value of x and t, psi of x and t must be have unique value. You can see the diagram on. This is the wave function. Everywhere, if you take the wave function at any place, it will be unambiguous. That is single value only. You can have single value. So this wave function is correct one. What about the next one? Here you have a wave function, two value. It's not a single value. Here one value and here one value. And at point P, you have here one value and here one value. So this is not the valid wave function. Then we will move on to further properties. As I said, the wave function and its derivative must be continuous everywhere. If a function has a discontinuity, such as step function or square wave, the derivative of the function will be either very large positive or negative number. Since the momentum of the system is found using the momentum operator, we have seen the momentum operator is minus I h cross, that is momentum operator is minus I h cross delta over delta x. So it is a position derivative. So since momentum function is a derivative, which is first order derivative, this would implies an infinite momentum, which is not possible in physical realistic system. Say I have given three diagram. First you see the one. This is Gaussian wave packet. This is continuous, and its derivative also. The wave function and its derivative must be continuous in this case. What about here? Triangular, sorry, not triangular, a rectangular wave. Here you can see there is a discontinuity here, and discontinuity here. That is, here you have positive discontinuity. Here one discontinuity, I will use different color. This is here you have discontinuity, here negative discontinuity. So this is not a valid function, and also here you can see discontinuity here. So if it is discontinuous, if you take the derivative, it will be infinite. Delta over delta x, in this case you can see that is delta y. Y is y is a large value, and delta x is 0 in this case. So this will go to infinite. That is, momentum is infinite, which is not possible in a physically realistic system. So the wave function and its derivative must be finite and continuous. Why it is continuous? Because as I said, if it is there is a discontinuity, the momentum will go to infinite. Thank you very much for watching my video and supporting me continuously. Thank you very much.